record this for the seminar for Jessica. She just sent me a link that she was not a co-host to this. So Dr. Fureby, you should be the co-host and you can share your screen with your presentation. I'd like to take the opportunity, since we're starting 15 minutes late in 1 hour session. Normally we have discussions, questions and answers after the seminar. We can put that later on for those grad students who have more questions than we have time allotted. I can set up, let's say, in half an hour to an hour afterwards for individual discussions with Dr. Fureby in this Zoom link, let's say starting at 1:30, if that's okay. So as long as you don't have too many questions and keep them up too late, remember that Sweden is 6 hours ahead of us right now.
Okay, thank you, Kenneth. Can you see my presentation here?
Yes.
Good, then hopefully we have had enough of technical problems. We have, I think, quite a few of these nowadays when we go to the digital platforms. And each of the programs have their own individual specifics there. So I think today we got some interesting new features by sharing things between Sweden and the US. I'm really happy to be here. I wish I would have been with you in Raleigh in the US instead. But I guess the situation is what it is, and we have to try and live with that. So I will try and share some views on novel propulsion and combustion concepts, not only for sustainable aviation, but also for sustainable power generation, I would say. Since there is a lot of commonalities between these two different areas. So I guess the key thing here is the interplay between energy and the environment. We need energy, and this is one of the corner pillars for prosperity and development. But at the same time, we're all aware of the greenhouse effects and that we're basically damaging the planet and also our environment by burning coal, natural gas, oil, and these kind of things that we're quite commonly used to burn to create energy. And we have this in both the heat and power and electricity sector and also in the transportation sector. And different sectors are making progress at different rates. And I think maybe the car industry, the car manufacturing industry is one of the industries that has advanced the furthest and is today moving rapidly into electric cars. Whereas perhaps aviation will be one of the sectors that will be more slow, at least, to transfer to carbon neutral fuels. And this is, of course, because of the complexities of the jet engine. And I guess this picture up here shows some of the global information that we have. We can see that the CO2 concentrations, they increase over time. The temperature, the global warming is increasing. And the main reason is, of course, that we're burning more and more oil, coal, natural gas, and so on. Our demand for energy is increasing. This is quite natural, of course, since the society becomes more complex and integrated. But at the same time, we have to work to try and reverse this trend. And we can divide also up the amount of energy being produced into different sectors. And then we clearly can see that the key or the biggest sectors is transportation, manufacturing, electricity production, of course, and they're dominating. So it's in these sectors that we have to make the biggest cuts here. Aviation, on the other hand, is not consuming more than a few percent of the world energy and is responsible for approximately 3 to 5% of the global warming. So that's not that crucial, but the problem is that the carbon dioxide being emitted is being emitted high up in the atmosphere, where it also makes the biggest damage here. So I will be talking about different ways of trying to kind of mitigate some of these effects, and especially what is done in Europe and so on. And the key issue is, of course, to replace fossil fuel energy production by CO2 neutral energy production. And that can be done in different ways, depending on different purposes, of course. We have a lot of power plants. Some of them are coal-based, and they're rapidly being replaced by oil, gas, nuclear, and then further on towards really CO2 neutral energy production, such as hydro, wind, and geothermal. And there is also a lot of additional work done to kind of make these power plants cleaner, like flue gas cleaning, and gradually moving into district heating, which I think we're pretty well off in Northern Europe in that sense. But we have also the transport sector. And there we see a very rapid transition from diesel and gasoline engines towards batteries, towards fuel cells, and towards hydrogen engines. And this is really an interesting phase to follow. But this is also something that is possible to do on road transportation. It, of course, becomes more and more challenging when it comes to construction equipment and heavy trucks and so on. But there is really a lot of research going on in that direction. For jet engines and power generation gas turbines, the process is more complicated, and especially for engines that are actually flying, simply because of the safety issues with changing fuel, and also the complexity of generating carbon neutral fuels with the same properties essentially as conventional jet A fuel. So this is really a challenge that we're facing. Also, aviation is growing very rapidly. This is a map showing roughly the air routes in 2010. And this is what happens when you look at what was expected to happen in 2030 without the influence of the pandemic. So there is definitely a big change ahead, even if our more digitalized world maybe will reduce the amount of aviation in the near future. I think this is a likely scenario to happen in 1, maybe 2 decades in time. And this is what we have to try and mitigate already now. And as I said before, aviation contributes roughly to 3 to 5% of CO2 and global warming, but roughly 35% of the trade. So even if it's not that big in terms of global warming effects, the influence of the society is pretty big. And the main issue is, of course, what we typically see when we look at the sky. We see the contrails, which is essentially ice crystals that are formed by the combustion products. And there is a number of ways to try and alleviate this. One is, as I said before, move from conventional jet A to some kind of synthetic or biojet fuel, and there are different ways to do that, but neither of them is very simple or well understood. But then we also have other options like going to electric aircrafts, and this might be a feasible opportunity, but then we probably have to restrict it to short routes, and then maybe trains is an equally useful transportation method. There is a lot of work going on also in terms of hydrogen, and I've taken two images here. One is the Cryo Plane, which is concept airplane developed in a EU project in Europe some 5 to 10 years ago, when they're looking into the possibilities of powering civilian aviation with hydrogen. And what you see is, of course, a large tank of liquid hydrogen on top of the passenger cabin. Potentially this might work, but the engines have to be completely redesigned to burn hydrogen, which is of course an issue. The other option is to change system altogether and go towards hypersonic cruisers. And this is from another European Union project called Stratifly, where we're looking into this kind of flight vehicles for long-haul flights. And then we're talking about flying from Europe to Australia in 3 hours using hydrogen. And essentially same ticket price as we would have on today's business class flights. So that's a very interesting alternative scenario here. And most of the engines that we will be having for aviation will be some kind of jet engine technology. And jet engines are well known. They have high efficiency, they're safe, it's a well-proven technology. And the key issue is there really which fuel to use. Do we need to modify jet engines to burn alternative fuels? For some, definitely yes. But there is also the option of combining research here with what is needed for power plants, because many power plants actually use aviation jet engines as the core. So yeah, this is kind of what I said before. These are the 3 different concept airplanes that are being looked into. We have the Cryo Plane, as I explained. We have an American company, Boom Supersonic, that is developing supersonic airliners. We're actually collaborating with them in an EU project that I will be talking a little bit about later on. And there we're focusing actually on both hydrogen and biojet fuels for their engines. And then we have the predecessor to the Stratifly project that I mentioned before, namely the LAPCAT projects, where we have over almost a decade in Europe looked into supersonic flights based on hydrogen. And this is actually looks more like very futuristic approach, but technology-wise, it's reasonably mature. There are some technical issues that remains to be solved, and we think it can actually be integrated into the airline system without any huge problems. So this is ideas for the future, basically. If we take one step back a little bit and think about the engine technology that we have at our disposal and what we think can happen in the near future, we of course have turbojet and turbofan engines. This is what we typically use today. And there are some interesting development paths there going towards open rotor, different engine cores. But I guess the key issue will be to change from conventional kerosene to some kind of biokerosene with similar but somewhat different combustion properties. Then we have afterburning turbojets and afterburning turbo ramjet engines, and this is what we see in fighter jets, but also what we saw in the Concorde airline, and this is what might be the key technology in future supersonic airliners. So they can kind of go up to Mach 3 in terms of speed. But if we want to go even higher, we have to go towards ramjet engines. And that's again a different technology, but still having combustion occurring at subsonic speeds. If we want to go even further, we have scramjets, and this is where essentially combustion occurs at supersonic speeds. And ideally, I mean, you would like to be able to traverse this range of Mach numbers seamlessly with one and the same engine. And this is really the problem, because turbojet engines type of work up to Mach 2.5 to 3. And if you want to go beyond that, the losses in the engine will be too large. So that's really not feasible. So then you have to have some kind of transition towards a ramjet engine. And that's quite a big transition step. And again, if you want to go further, you have to have another transition step into a scramjet engine. But that is at least believed to be able to be maintained within the same engine duct. So basically, then we're talking about a dual mode ramjet engine that can operate both in a ramjet mode and then transition gradually to a scramjet engine. And ideally, these engines don't really have any moving parts, whereas the turbojet and turbofan engines does. So if we really want to be able to explore this range of velocities that we're talking about here, we need to develop something that can actually integrate both a turbojet engine and a dual mode ramjet engine. So basically a turbine-based combined cycle engine. And this kind of engine concept is really what we have been exploring in the projects that I mentioned before, LabCat 1, LabCat 2, and now also Stratofly. And of course, it's technologically extremely challenging, but we really think it's possible to make these kind of engines operate and work. But also more recently, there has been some rather different developments in terms of rotating detonation engines, which is a radically different concept, exploring detonations instead of deflagrations as a propulsion concept. And RDEs also seems to have a very big potential for future power generation and propulsion technologies. So we've talked about different engine types, some pros and cons, but there is of course also the issue of which fuel you're burning and how complicated that fuel is to burn. What you see here is really a footprint of conventional kerosene. And it consists of a number of different hydrocarbon molecules, average about C14, something like that. And it's a mix of different types of hydrocarbons, paraffins, aromatics, and so on. And the interesting thing is that the engines are really developed based on this fuel. So if you're changing the fuel, ideally you also would like to change things with the engines. It can be simple things such as such as the spray injectors, but it might also need to change other things. And what we talk very much about today is biojet fuels, or sustainable aviation fuels. And this has been discussed for quite some time, and there is a wide variety of ways to produce these kind of fuels, and from different feedstocks. For example, we can use various kinds of fats, we can use algae, we can use forest residuals, etc., etc. And depending on which feedstock you use, and also which processes, chemical processes you're using, you will end up with different types of fuels. And the footprint for different fuels is quite different. And I'm showing here two different examples. One which actually comes from forest residuals, and it has a lot of aromatics in it. And the other one is more similar to conventional jet fuel, and it comes from a Fischer-Tropsch process. So this is really a challenge, because we want the fuels that we develop to be similar to the conventional fuels that we're using today. And that can be done by mixing different type of fuels and fuel sources here, but that ends up being very expensive. The other side is that we actually go for a biofuel as is. Then we probably have to do something with the engine technology. So this is really a very complicated situation, and I think it will need a lot of research in the future to deal with. And then we also, of course, have hydrogen, liquid hydrogen, and I mentioned that in terms of the Cryo Plane and the Stratofly engine. But if we want to use that as fuel for a gas turbine or a jet engine, we need to think carefully about how to do that, because the flame speeds for hydrogen is much higher than that of conventional kerosene-based fuels. And that will again require some different types of engine technologies. So, okay, so we have a number of challenges ahead. What tools do we have to investigate these? One is, of course, small-scale experiments and corresponding simulations. And this is where we can use non-intrusive laser diagnostics, for example, to investigate the details of a flame. Similarly, we can extract detailed information about fuels, we can develop reaction mechanisms, and we can do simulations rather cheap to actually test that these mechanisms work and that things burn the way that we think for in a laminar flame configuration, in a weakly turbulent flame configuration, for example. So that's one option, and it really governs the small intrinsic details. But then when it comes to more complicated situation, which is approaching how an engine operates, it becomes all of a sudden much more complicated. The experimental apparatus to be used is much more complicated and larger. We can still use non-intrusive laser diagnostics, but it's not always the case that we can kind of look into the combustion chamber where we would like to do it. So we might be very much restricted in terms of fields of use. And then finally, we have CFD methods that can help us. CFD methods is not really telling us the truth, as experiments do. They give some approximate picture of the reality as governed by the equations. There is often a lot of models that we have to supply. I've talked about reaction mechanism, but also turbulence models and things like that. And they will require rather large computational resources if we want to apply them to big problems. So I guess the real future here lies in being able to combine these different sets of tools in the most intelligent ways. So we should use safety, but we should also use experiments. And I think they are both equally important, but should really be used together and with care. And I will be showing some results where we actually look at cases both from an experimental point of view and a computational point of view, and try to extract information based on both in the best way possible. So in terms of computations, there are different ways to do that. Direct numerical simulation is, of course, the most exact, but it's also the most expensive. RANs, Reynolds average Navier-Stokes models, perhaps steady-state RANs, is the simplest approach that give us the most coarse-grained view. And somewhere in the middle, we have large eddy simulations, which at least I think would be the most appropriate tool, a computational tool for investigating reacting flows. And in this methodology, we essentially filter the reactive Navier-Stokes equations over small regions in space. And the smaller we make them, the more exact the model will be, but the more expensive it will be. So this will be a trade-off between computational cost and accuracy to some extent. And we have to feed these models or these equations with models for the flow physics, essentially, that we're not resolving. So the subgrid stress and flux terms, which basically deals with the unresolved transport terms, they have to be modeled. We have to model also the filtered reaction rates or the influence of the chemistry. The chemistry typically occurs on very small scales that cannot be resolved, and therefore we will get some kind of coarse-grained chemical source terms that will enter the species equations. And the effect of turbulence there on the chemistry needs to be modeled. And this is a very complicated thing to model, simply because the chemistry is so non-linear. And we really don't understand how to do the reaction rate modeling today, whereas I think we have a pretty good idea of how to do the subgrid stress and flux terms. And this is really where we usually stop talking about modeling. But we have additional processes that we often forget, and one of those is radiation. So typically we're talking about flames that have temperatures on the order of 2000 Kelvin or something, and they radiate a lot of energy. And they enter the energy equation. So this is the term that we need to think about here. And without talking about things that we're not resolving, we just simply talk about the basic flow physics on the resolved scales here. We really need to think about how to incorporate thermal radiation in a simulation. It changes the temperature field, and it changes the interaction between different regions of a flame. And this is equally important for furnaces than for jet engines and Ram Scramjet type engines. And there are two different ways to do this. One is spherical harmonics based model, the P1 model. And the other one is discrete orders methods. And the P1 model is probably a reasonably good compromise. And at least I think it's better to actually incorporate that part of the physics using a simple model than simply neglecting it. So I will not say very much about this, but I just want you to be aware that there is a very wide range of LES or turbulent combustion models for LES. And I tried to make a schematic of it and group it for infinitely fast chemistry, flamelet, finite rate chemistry, premixed, non-premixed, and partially premixed. And you can really see that this is a complicated chart to understand. And there is a wide range of models, which each and every one have their own pros and cons here. And it's not really easy to select the right models. I've grouped them here so that the models on top, they're computationally rather inexpensive, whereas the one towards the bottom are more expensive. Whether it's the case that the accuracy goes in that way as well, that's not as easy to say. And that unfortunately depends a little bit on the case that you're looking at. And I think a lot of the modeling research that we do in LES today is actually focusing on trying to understand how different models work and where to use different types of models, and how can we rely on the basic underlying assumptions of these models. Yeah, I will not talk about the individual models here, but I think this is quite important to have a clear view of this difference in terms of models. Numerics is of course also another key ingredient here. And it's equally important as modeling the reaction rates or the modeling the turbulence part. And the numerical tools that we're using must be well adapted to the problem that we have. And typically we're talking about 4 different types of phenomena that we want to be able to incorporate and develop accurate numerical schemes for. One is, of course, convection, which is transport phenomena. And they're challenging because we need to avoid wiggles and over and undershoots. And to do that, we typically add a little bit of diffusion, but we also want to avoid adding diffusions. It typically overwhelms the small scale turbulence. So that's really a challenging trade-off to develop good numerical schemes for that. Then we have diffusion. Diffusion is not that complicated and can be dealt with rather easily. But then we have chemistry. And chemistry is a highly localized process, and it incorporates a very wide range of timescales. So this is typically something that we want to decouple from the flow simulation. And we typically use operator splitting to do that. And then we use carefully designed time integration schemes for solving stiff ordinary differential equations to deal with chemistry. But then there is a fourth phenomena as well, and this is the wave physics, basically. So in the equation, we will also have wave processes, and acoustic waves is typically one of them. And the numerical schemes also need to be able to capture wave processes in a good manner. So this is rather challenging and becomes very technical very soon, very quickly. And a tool to help us with understanding the numerics and especially the influence or the influence of the numerics on the physics is modified equation analysis. And this is a tool by which you go back from the discretized equations to some physical equations, but the terms that are there when you have done this process and was not there from the beginning, they describe the leading order truncation error. And this is basically the indirect effects of your numerical scheme. And this is something that is you need to be very well aware about and understand the influence of. So chemistry, yeah, that's another topic, really a topic on its own. And I'm showing laminar flame speeds on top and ignition delay times on bottom for methane, Jet A1, and hydrogen. And the symbols and the black and dark gray lines are from experiments and detailed reaction mechanisms, whereas the different colored lines are different simplified reaction mechanisms. And if we take methane, for example, now let's go directly to kerosene. So if we talk about the flame speed here, the black line here is a detailed reaction mechanism for kerosene. It's about 5,700 reaction steps. And that is far beyond what we can put into a CFD model. Like 10 years ago, we used 1 or 2 step reaction mechanisms to deal with this. Typically, this line here, the magenta line, or if it's carefully tuned for a specific target, this line here. But then it will work only for this typical operating condition. But today, our knowledge has improved quite a bit, so we can use pathway-centric or skeletal mechanisms that incorporates the main features of the large mechanisms without incorporating the details that are not that essential. And this is very much the case for a fuel like kerosene, where you have to take into account ignition delay times that has this kind of behavior. And it's only the detail mechanism and one or few of the skeletal mechanism that can do this. Otherwise, you overpredict or underpredict the ignition delay time quite a bit, and that will not really work when you're dealing with applied simulations. Talking about hydrogen, well, first of all, we say that the laminar flame speed is much, much higher than methane or Jet A. It's almost a factor 10 higher. And simply this knowledge tells us that hydrogen is not very well suited for an ordinary jet engine. Typically, it will generate flashback and things that we don't want to have. And also the ignition delay time is very different. It's much lower. So it really facilitates engines like Ramjets, Scramjets, and things like that. So different fuel fits different engines in a very different way. So the big challenge really comes when we want to look at biofuels. So biojet fuels, for examples. And we would like to test these in engines, but we want to know exactly what happens before we test them. So basically, we have to develop reaction mechanisms based on that. And for that, we need to use these simplified reaction mechanisms, such as this pathway-centric mechanism, where we only kind of focus on the most important part of the reaction system. And we have done that, especially when I was at FY, we did quite a significant work on that. And we developed a methodology whereby we break down the combustion process into different subsets. And we could actually freeze the CHO chemistry part and make that work for basically all different types of fuels. And then as higher and higher we come in this chain, we of course have to adapt the fuel breakdown reaction parts to the actual fuel that we're dealing with. And this really becomes important when we're talking about or changing from fossil jet fuel combustion to biojet fuels. Because as I showed before, biojet fuel has a very different footprint. and we have to be careful when taking that into account properly. So this methodology here will have a possibility of providing us with sufficient information to run biojet fuels properly. So now I've talked a lot about models and model development, chemistry, and so on. So how does that actually work when we apply it to something? So this is one test case that I've used a lot. It's an afterburner type geometry. And you're looking at two short animations of propane burning, lean propane. The two cases have different temperatures, 280 and 600 Kelvin. And this is why you see a very different type of combustion behavior. You're looking at heat release on top, various species, and axial flow velocity. And this is an ideal test case for comparing mechanisms and models. And these two images here, they show temperature profiles at different cross sections. And the symbols are experimental data. And the different lines and different colored lines indicate different reaction mechanism to the left and different combustion models to the right. And clearly we can say that the simple reaction mechanisms and also the more simple models, they do a less accurate job in predicting the temperature profiles than the more advanced mechanisms and the advanced models. But the advanced models and mechanisms are also more expensive. So being able to understand the limitations of the modeling and the reaction mechanisms and the interplay between these becomes all of a sudden very, very important. We have done similar studies in a variety of cases. This is a gas turbine combustor burning methane, experimentally tested at DLR in Germany. And if we're looking at the profiles, we essentially see the same thing, although the flow is very, very different. Again, a strong dependency on both the reaction mechanism and the model, but also clearly that the reaction mechanism is very important. And if you don't get the reaction mechanism right, you will not be able to compensate for that by having a more advanced or better turbulent combustion model. So this is really quite a lesson, I think, for us. We can take this to high-speed combustion as well. And this is part of the EU project Stratofly, where we have experiments conducted at ONRA. You can see the test rig up to the left. It's a direct connect facility. And we're burning hydrogen, and hydrogen is being injected both in the upper wall and in the lower wall. And we're interested in trying to find out limitations for different operating conditions here. And this has been a very close collaboration between experiments and simulations. And this is one case where we have a comparatively low stagnation temperature at the inlet. And then combustion occurs quite far downstream, roughly where the flows start to separate. You can see that here in the experimental image as well. Then we increase the stagnation temperature, and we clearly see that the combustion creeps up along the wall, and it starts somewhere here. It actually oscillates a bit back and forward. It does that in the experiments as well, which is quite interesting. But it's also extremely sensitive to details here. we found that we had to incorporate also effects from a rough boundary layer. The experimental combustor had a zirconium oxide coating with a rather significant roughness factor, and that's something that we had to add in the simulation in order to get good agreement. So this kind of shows that it's very, very sensitive to even small details. Increasing the stagnation temperature even further, we have a very different process. We have shock-induced combustion or shock-induced ignition. And it's very interesting to see that the numerical simulation models, in spite of all the modeling that goes into them, are actually able to capture these three different modes of operation. And I think that's a very strong indication that simulations are doing a rather good job. In spite of the shortcomings, we know that many of the models or submodels have. And of course, we have looked at not only quantitative, but also qualitative comparisons, typically at the wall pressures. I will skip this case. So now I want to spend a little bit time talking about this EU project Stratofly that I've been mentioning before. And it really tries to investigate or tries to help us to reach rather high TRL levels in understanding of dual mode Ramjet air transportation systems. And this will not solve all the problems, but it might be one step towards helping us reach the goals of shortening the distance across the globe and at the same time reducing emissions. So it's funded by EU. We have 11 partners from 7 different countries. We have an overall budget of around 4 million euros, and the project have been running for initially 30 months, but we had to extend it due to the pandemic until 36 months. And we're doing experiments and we're doing simulations jointly. And the business case that we're focusing on here is actually Europe to Australia. And today we go by conventional airliners. There is a specific or a certain environmental impact on this, of course. And there is also impact on us when we travel because it takes 20 plus hours. The concept that we have developed is using a dual mode Ramjet powered airplane. Quite different, looks like a flying brick perhaps. Flight speed of around Mach 8, 300 passengers, duration 3 hours. And one of the constraints is that the ticket price should not exceed today's business class. And we have been investigating this concept to see if it actually works. And although the project is not really ended yet, I think we can safely say that we can definitely reach the goals, even that of the price tag. We have been working with with a concept vehicle, which looks like this. This is a cutout. So basically you have a passenger cabin, you have an engine duct that goes through it. It's a dorsal mounted engine. I will show a zoom up of that later on. And around that you have a lot of liquid hydrogen tanks. It's a different type of airframe. It's based on a bubble architecture to make it sufficiently strong, whilst being of a different type compared to conventional airplane. The propulsion system looks essentially like this. So there is a scoop-shaped intake. Then there is a DMR duct And on the side of this duct, there are 2 air turbo rocket ducts that contain 3 air turbo rockets each. And these air turbo rockets are used for takeoff and landing, whereas the dual mode ramjet is used for cruise. And this is like the intended operation. And primarily, the cruise will occur at an altitude of 28 to 35 kilometers roughly, so in the stratosphere, using the Scramjet engine. And the environmental impact of the Scramjet engine is quite interesting because it will produce a lot of water vapor, and we're quite concerned about water vapor in the stratosphere. And we're also concerned about the NOx emissions. And other interesting aspects is, of course, the transition between the ATR and the dual mode ramjet engine. So to understand this, we have done combined experiments and simulations. The experiments are done primarily at DLR in Göttingen using their shock tunnel. And this is a picture of the actual shock tunnel. So you can see the different piston systems. And you can see that down here, we have an actual test section, and you have a dump tank here. And this can actually provide us with the correct operating conditions for a downscale model of this flight vehicle that we can test for about 0.4 milliseconds. But there is a short duration, but it will be the exact correct operating conditions. And in this test section, we have actually manufactured and inserted a downscale model of this flight vehicle. And you can see it here in the green, inserted in the test section. And the test section has a number of windows, so we actually have optical access to this. And the test section is supported by Kevlar wires. And these Kevlar wires are actually cut when the flow is coming from the left. So the experiment will be of a downscaled version, but it will be free flying. And here we can actually test if the dual mode engine actually ignites, and if it burns, and if it produces thrust. So this is as close as we can come to actually flight testing something. And the data that we will get is somewhat limited, but still quite interesting. Pressure data on the walls, and also heat fluxes on the lower wall primarily. Simulation-wise, we have generated a close replica of this. And you can see the flight vehicle. There is an intake, there is a first combustor section, there is a second combustor section, and there is a nozzle. There are 3 struts, 2 semi-struts and 1 full strut. And at these, we inject hydrogen. Most of the hydrogen is injected in the front strut, on top of the front struts, whereas the remaining hydrogen is injected in the central strut further downstream. The hydrogen is quite cold. It's 167 Kelvin, and it's cryogenic from the beginning, but the aim is actually to cool the combustor before injecting it. We're looking at different operating conditions, different flight altitudes, so 27 and 35 kilometers with quite low static pressures. And from a numerical point of view, we've created a number of grids ranging from 12, 45 and 90 million cells, something like that. And due to the very low running time of the experiment, we're fixing the wall temperatures. That will, in a sense, allow us to compute the wall heat fluxes instead to compare with. And another thing that we're using is that we're using wall model LES. So basically we have a subgrid wall model to cater for what happens just adjacent to the wall. And this is something that we have essentially borrowed from other areas as well. So some results. This is a volumetric rendering from the side of the axial velocity field. So the flow is from left to right. You have the intake, you have the two different combustor sections, you have the nozzle. And the flow here is roughly at Mach 8, so 2,400 something meter per second. And you can see the semi-struts and you can see the full strut. The semi-struts, they have two injectors on top. The full strut has two injectors on the top and two injectors on the bottom, on the side, on the lateral side, so to say. And what you can see is that you will have a compression. You don't really see it in the velocity, but you will have a slight decrease in the velocity here. And then you will have a significant decrease in velocity here. And this is, of course, due to that we will have combustion occurring. So there will be volumetric expansion and something similar to thermal choking if we have too much fuel there, but not in this case. And then we will have gradual acceleration, and we will basically have a positive net thrust, both numerically and experimentally for this case. This is the corresponding temperature renderings. And here we have really cold flow, and you start to see that there is a boundary layer growth, there is compression, there is some temperature increase. The flow in the towards the end of the intake is very complicated. It will be dominated by two longitudinal vortices that stretch down in the combustor and multiple small-scale vortices. There is a vortex pair developing along the intake, very close to the center line, that will change the flow field quite a bit around the semi-struts. There will be some ignition taking part in this initial part here, but it will be mainly dominated by low temperature chemistry. Then further down, when we have this full strut, we will have an additional set of shock waves, and we will have additional fuel, and then we will have very intense combustion going on here. That will gradually cool down as we expand through this second part of the combustor and through the nozzle. The pressure is also extremely complicated. It's very difficult to get a good representation of that because we have curved three-dimensional shock waves throughout the combustor. But the main pressure rise occurs here, which is also where we see most intense combustion. These are images from the top, and we actually have experimental images similar to this from the top, showing what happens with wall heat fluxes. But I think it can be quite interesting to see what happens with the flow in this direction. And the walls are colored by the pressure, and then you can see the hydrogen being injected here from these two semi-struts. And then also from the full strut, you see hydrogen being injected here and here. This is volumetric rendering. So basically what you see that is you have high amount of hydrogen here, and it gradually both dissipates and gets consumed. So far downstream here, we have very little hydrogen. And this kind of suggests that the efficiency here is reasonably good. Next, we look at low temperature chemistry. So that's HO2 being representative of that. And we clearly see there is some remnants of HO2 already here. So basically the shocks covering the semi-struts will at least partly ignite the hydrogen. But then due to the very high speeds, we really don't see full combustion starting to occur until far downstream here. So the ignition delay time of hydrogen is quite important. And that needs to be paired against the very high velocity through combustor. And here we have the heat release. Quite intense heat release around the shock waves from the hydrogen injection. Downstream, it's a very elongated structures. And then we have again hydrogen injection, a very complicated heat release profile, strongly coupled to the shock wave system in the combustor.
Dr. Fureby, I just want to point out that we're about 15 minutes overdue, and we have target Czechy scheduled for discussion afterwards.
Yeah, I was just about to wrap this up.
All right, thank you.
So here we have the water vapor being produced, and this is actually a problem that we're producing a lot of water vapor, since we really don't want to emit too much water vapor in the stratosphere. And also the other issue is NO, and NO appears to be less crucial for this case compared to what we estimated. And primarily there is no NO being formed in the low temperature region, whereas it forms further downstream. This is also a picture of the temperature. So basically it's quite complex, and it shows remnants of shock interactions and so forth. And we are able to compare computed and experimental wall heat fluxes, as we can compare pressure data along the upper wall between the simulations and the experiments. In the pressure data, there is a blue line and there is a red line corresponding to non-reacting and reacting simulations. So basically the impact of combustion here is quite significant. And again, we see that the simulations is really doing a pretty good job in capturing these differences. So thank you for your attention. Thank you for listening to this presentation.
All right. Thank you all for attending. Since we're about 15 minutes overdue in intruding into the discussion slot that Dr. Fureby has with the other faculty, what we can do is, as I mentioned in the beginning of the seminar, we can have reserved about an hour or so, half an hour, of student discussions and questions with Dr. Fureby from 1:30 onwards on this Zoom link. That's when our faculty meeting starts. So the faculty will be busy doing other things. So with much further ado, thank you, and can I ask the students to log off from this Zoom link, and you're welcome back in again at 1:30. And we'll continue with the faculty, with Dr. Czechy, Dr. Eckert, and Dr. Fang in succession. If you want to rearrange times, I've removed my name from my time slot at 1 to 1:30. If you want more time.
Good evening, Krister.
Hello there.
How are you?
I'm fine. How are you?
Good, good. It's a pleasure. I wish you were here physically.
I would like to have it there. You know, I've never been to Raleigh.
Well, hopefully once the pandemic is over, you'll have the chance to do that.
I really would like to do that. I really would like to come.
Yes, yes.
I
I
think
really
also-
enjoyed your talk, by the way.
Sorry?
I enjoyed your talk. It's always kind of interesting to it is interesting to have a window to the applications. I've kind of been staying more on the laboratory kind of scale, kind of work modeling and to see
we
that
need to
work.
have both. I think we need to work with both.
Yes, yes.
I mean, doing the application thing, it's always fascinated me, but it's always challenging, but puts things in a different context and so on. And I think when we start doing applications, we really see what the methods that we have can help us with and what their constraints are.
Yes.
And that can give us new motivations to develop them further.
Yes. Yes, I totally agree with you. And it's always, to me also, I think you presented some results on the challenges of having to deal with chemistry and at the same time also turbulent closure for the especially for heat release and reaction rates. And I always kind of struggle with the idea whether it's really a question of pushing the turbulent combustion closure model or pushing the chemistry, and it's almost leading me toward this whole idea that you have to have chemistry adapted to a specific configuration, a specific problem. Because you can have, you can have chemistry, you can have a detailed chemistry, but maybe you're doing EDC or something, and maybe you're not capturing a lot of the the turbulence kind of chemistry interactions and stuff like that. But I'm curious to see also your point on that. And
but to some extent, I think chemistry is a lower hanging fruit to pick.
Yeah.
Simply because we have experimental data, we can do laminar flame speed and ignition delay computations, and we can develop mechanisms based on that.
Yeah.
But we need to expand it beyond that. We need to take into account extinction strain rate and so on and so forth.
Yes.
But that's still doable, I think. When it comes to turbulence chemistry interaction, there is so much we don't know.
Yeah, yeah. I totally agree, and I think I mean, to be honest with you, like my general perspective on these is that, the probably the way forward on a lot of these methods. I mean, if you say, let's say, I'm going to use flamelet, you are going to be restricted by, as I said, maybe ignition delay, maybe extinction strain rates. So one has to come up with maybe one of those low dimensional stochastic models from PASR to LEM to ODT, and kind of create configurations where you can reproduce at least some information about the composition space, and then you can do your chemistry reduction on that data.
Mm-hmm.
Then when you come in and do some fancy flame generated kind of flamelet generated manifold or something like that, you are at least capturing that composition space reasonably well. And the chemistry reduction probably has to be done on that data. And if you specify that you're doing chemistry reduction on the data, you can be more aggressive. Because it is adapted, it's fit for that data.
Mm-hmm.
But it's still, I think, something kind of on the sideline. I mean, it's not. I think most of the focus, I think, in the industry is probably on existing models. The existing models, not database models, but kind of the flamelets and FGMs and whatever is really available on the standard CFD codes, right? So that's kind of where the challenge is.
Yeah, but I also think we need to pay attention to incorporating all the different processes, like I mentioned, radiation.
Exactly.
I mean, if we have a setup that we want to improve by improving the turbulence chemistry interaction models, and we don't really have taken radiation into account, I think that might be misleading.
I agree. I agree. So you
So-
sort of have to have turbulence chemistry, and then you have turbulence radiation interaction to deal with. Yeah.
Turbulence radiation interactions might not be that important actually, but at least having the radiation part in the CFD simulation, I think, is important.
I agree. I agree.
But yeah, I mean, I'm kind of, I get around this several times, but now I think I'm at least more mature to continue with the next set of turbulence chemistry interaction models.
Mhm.
And for that, I would really like to do work on multi-scale methods. Not any simplifications there, but real multi-scale methods, like based on homogenization-based theory and something more mathematical. Because I mean, I can say that I cannot really say that we can advance things further with these empirical models. I think we need to revert back to the math and incorporate some of the more sophisticated tools from there.
I agree. I mean, it's like, sometimes I liken it to, getting some really nice suit, and then with time you start patching it because it's getting older. At the end of the day, like after 10 or 15 years, the suit is basically just patches and not the. So you can add all kinds of fixes to planelets and to other existing models, but at one time, it's basically easier just to go back to the drawing board and come up with something that is more fundamental, as you said, like a multi-scale, maybe coupling LES with, like the NEM LES ODT kind of approach, where you actually are coupling a low-dimensional model that captures the subscale physics directly without any closure, and then couple it with LES, for example, or something like that. I mean, they're expensive, but there may be ways of reducing that. I mean, people are talking about, using a deep learning approaches or something like that. Maybe you can, run the problem in different places and then develop the data and then eventually switch to a parameterized kind of simulation that's based on simulations and different, grids or something like that.
Yeah, but I think the challenge, at least here in Europe, is that now funding agencies that they know roughly what you can do.
Yeah.
And then if you say that, okay, we want to go back and develop a more sophisticated models, then you run into problems there.
It's the same thing here. It's the same thing in the US. I mean, people have heard researchers for a long time promising to come up with a new approach. And they've been funding them for a long time, and I think there's fatigue. So it's the same thing. It's the same issue. And,
yeah, exactly.
Yeah.
It must be, but I think it's necessary that we start thinking about taking this next step.
Yeah.
And as you mentioned, I mean, AI and deep learning and these kind of tools are now available to us.
Yeah. And we do generate data. We do generate data at all levels. We generate data on the laboratory scale. We generate data on LES with kind of medium size. And if you have multi-fidelity data, it's still useful. And it can be fed into the larger scale if you want to. So that's where I think the AI and deep learning and all that can come in to save the day. Well, I mean, it should be explored at least. I don't know if, I can't promise that, but it's an interesting problem,
But I think also, I mean, with the transition that we're facing now, I mean, going from fossil-based economy to a CO2 neutral economy.
Yeah.
I mean, we will not get rid of combustion engines.
It's not going to be practical, at least as you said, for aircraft engines, you can't just, I don't know how easy or practical it is to just run it on battery, for
there were some interesting concepts tested in Europe. I mean, there is a high-winged airplane with 4 engines, and they're talking about replacing one engine with an electrical engine instead. and testing that, because they're not jeopardizing the safety.
Yeah. You have a backup. Yeah, it's like the hybrid cars on the road, right?
The downside is that they can't take any passengers anymore because the weight needs to go to the battery.
But it looks good otherwise.
Yeah. No, but I mean, electric and batteries, they also have their drawbacks in terms of the metals that they're using and minerals and so on.
Yeah, with large batteries, I think there's a lot of environmental kind of risk, and also where does that energy come from? That's another thing too. So you have to, you sort of have to look at all the sides, right?
Yeah.
I don't know if you met Srinath.
I'm Srinath, and I'm the department head here. Also in the propulsion area, kind of.
Hello. I don't think we have ever met, right?
No, I've been to London, and actually Bent Sundon had invited me, and I went for a defense PhD defense in his department many years ago, 2016 or something like that.
Okay. I've taken over from him because he was the division head and heat transfer before.
That's right. Yeah, he was stepping down just when I got there. One of his students, and I was on the defense of his students. I was the external person, sitting there. So this was about 2016, if I remember right. Yeah, pretty nice. It was fun. Enjoyed the visit. It was really good to be there.
I think Lund is a pretty nice place. It's a nice city. Typical student city.
Yeah, that's basically what I do, gas turbine heat transfer, which is what Bent also does a little bit of that. So
yeah.
So we've been I was watching a talk in the last part, because first part I had a sponsor meeting, so I missed the front part, but I was watching all the LES stuff, and I'm pretty sure Tarek was very excited about.
Really interesting stuff. I always enjoy listening to Chris there, because I think you kind of straddle. I like the way that you straddle the fundamentals and the applied, which is really not an easy thing. It requires large groups, and I think you've been successful in doing that. So I really appreciate you.
Yeah, we currently have this big DOE initiative on hydrogen combustion. So Tarek and I are actually trying to pump out some proposals on hydrogen and hydrogen blended ammonia combustion. So hopefully we'll get some funding on that, and we actually can make some. I have a combustor rig where I can do blended fuel gaseous combustion.
Okay. Yeah.
So I've been doing that for Solar Turbines, which is a small company. I don't know.
Yeah, well, I know them.
So they gave me a swirler nozzle many years ago, and we built a combustor around it. And it's an 8-inch can combustor. So, but you can actually see it because it's all quartz. So I can do PIV measurements, infrared measurements. So we have done a lot of that activity in the past 6 or 7 years. And when this new proposal request came from DOE, so I said, well, Tarek can help me guide my experiments a little bit better with some more CFD and analytical stuff on the combustion side that can help us with the experiments, right? So that's what and also understanding the chemical kinetics a little bit better. So we are starting to work on that area. So hopefully, but I heard recently, actually, yesterday there was an announcement that there's going to be a little bit more push from Air Force and NASA to see if they can get hydrogen combustion in the aircraft faster. So I don't know how fast, but they're planning. They just announced it yesterday, so we'll see how long it'll take before they put in some money into that.
Yeah, that's interesting. I mean, ammonia on one hand side and hydrogen on the other. They're very different as fuels. I mean, I have experience with mixing hydrogen and methane and investigating that. And that's a very interesting change between when you approach, I don't know if it's 50 or 60% or something. It's almost like a jump in flame speed.
That's exactly what we are trying to do with this part of the proposal, is to start mixing hydrogen with methane, with the idea that we'll go with 5%, 10%, and also the question the challenging question. Ammonia has blowout problems and hydrogen has flashback problems, right? So we have to come up with the right consistency. And I mean, there, of course, the challenge, will the fuel nozzle design change? How do we accommodate for flashback and hydrogen, but at the same time, maybe have a pilot flame, which is maybe a hydrocarbon to keep the ammonia side of it, if you're ammonia to keep it going, flame going. A lot of interesting questions to answer, especially in blended fuels. So we just wrote a big DOE proposal. We are hoping that we get picked so we can actually solve the problem.
About 10 years ago, maybe I worked a lot with Siemens on this hydrogen methane combustion, and we did big campaigns, experimental and computational, looking into this, and we played around with the amount of hydrogen that was blended into the methane, and there were some very, very funny behaviors, some stages there. But I think it's very much related to this very sudden jump in flame speed.
Yeah, that I think that we are going to approach that very cautiously.
Yeah, especially experimentally.
Yeah, that's right.
I mean, we had one instance where we actually did simulations before we actually did the experiments, and we found that we got at some operating condition, we started to get flashback in the boundary layers in the fuel nozzle, basically, in the mixing tube. And the experimentalists, they were, yeah, that doesn't really happen so quickly. And when they actually did the experiment, it happened.
Yeah.
So that was very interesting to see that also in the experiment, that it really starts in the boundary layer in the way that it did, and starts propagating upstream in the mixing tube.
Yeah. So
gentlemen, maybe I'm stepping onto your time, Srinath. So I'll.
No, that's okay. Stay on. That's okay. Stay on. We can talk. I mean, it's all the same thing. There's no time. Yes, talking technical stuff. It's fun. It's like good stuff.
Okay.
I mean, I have to leave anyway at 12 o'clock, so I have another thing, and then we have a faculty meeting at 1:30. So, so this is our once a month faculty meeting. So we have share information with the faculty and all that stuff. Yeah. So are you guys back in the office and the lab and
No, I mean it's a pretty bad situation in Sweden. I guess you have followed the news and everything.
Yeah, you guys decided not to do anything, right?
Well, we have done things, but there are different views on this. Typically, I think Swedish people follow the guidelines much more rigorously than many other people in Europe. So I think the anticipation was that we were going to follow the news and follow the guidelines without having to do any strict things. And that worked in the beginning, but it's not working as good now, I think, simply because people are so sick and tired of it.
Same everywhere. The US. Somewhere in November, everybody gave up in the US. And they just went up 200,000 people a day, almost ridiculous.
Yeah, but this is really difficult because you don't really know how dangerous it is and how it spreads, and there is so much we don't know about this thing.
Honestly, on our university campus, we have realized that the kids get it and they're fine. Nothing happens to them. A majority of them, 98%. Nothing happens. It's the problem is the other 2% is unpredictable. Like you said, who is going to be having the severe symptoms, and who will potentially end up in a hospital? It is no clear guidelines on what this thing does to you, right? So that's where the challenge is. The challenge is how do we ensure that nobody is in that serious zone.
It looks like we're doing well, right? I mean, the positivity rate is less than 2%.
Yeah, on campus, yeah, less than 2%.
I have to test every week, even though I don't show up to campus. I have no idea why.
Yeah, I go there. I just went in the morning actually at 9 o'clock today. Got tested and came back.
It's not crowded. It's actually you walk in and all that, and you just do it less than 5 minutes, and you get the results the next day or 2 days later. So it's okay.
But do you guys work from your offices or from home, or mix?
I am actually in my office right now. So I come every day about a few hours. I mean, there's not much traffic in the building, so it's pretty convenient. It's about maybe 15 to 20% people in the building compared to what it would be normally. We don't have in-person classes for our undergraduates. So it's only the graduate students you see in the building mostly. And also we do have some undergraduate. We have asked students if they want to come to labs, like undergraduate laboratories, then we allow them to come. And our senior design, in the senior design is face-to-face, but it's controlled face-to-face. So they come only during a 2-hour window during the week. And there are only like 10 or 12 kids in the entire big room. So
Yeah.
we are doing whatever we can, luckily, and the students are required to test. So every week they have to show the faculty member that they have a negative test so they can come back into the building. So
Okay. You actually test as well. We don't do that. I mean, the testing is not that extended here.
what about the vaccine? What about the vaccine situation?
The vaccine situation in Europe is not very good, I think. There are too many delays in the production.
Oh.
Okay, I think they were marvelous in actually finding